Today's lecture is going to be on glacier dynamics. We're going to look at how glaciers form, flow, and evolve. So what is a glacier? Well, glaciers are slow-moving masses, or rivers of ice, due to the accumulation and compaction of snow into ice. There are two types of glaciers: alpine, sometimes called valley glaciers. These are found in high elevations on mountains. And here's a picture of this. And continental glaciers are masses of ice that are much larger than alpine glaciers. Small-scale continental glaciers are called ice fields, and large-scale sizes of ice are called ice sheets. So a glacier forms as snow accumulates to depth, about 65 feet, and flows out from its own weight. So the process of snow accumulates, it gets compacted into ice, denser than snow, and then it recrystallizes into a much deeper, denser type of ice. So here's a picture of a continental glacier formation. Here's an alpine glacier. Notice they both have the accumulation zones. Here's the zones of accumulation. They have a melting or ablation. Ablation is really the loss of glacial ice. It could be melting, could be sublimation. We're essentially losing it on one end, generally called its terminus, or the end of it itself. And it can also be calving. Sometimes an alpine glacier flows into a body of water, so calving can be another process. So you have this net accumulation. It then flows outward and eventually has an ending location to it. Here's a schematic of an alpine glacier. It has the zone of accumulation. I want you to pay attention to these arrows. These are the net movement of this kind of ductile, deep part of the glacial ice itself. And we have these crevasses. We have the direction of the ice movement is from uphill to downhill. Gravity is your driver here. And then we have the zone of wastage, or in this case, we can call ablation. And then here at the end of it, you generally get streams of water that are just the melt water from the glacial ice itself. So here's your alpine glacier, where gravity is your driver. So we're going to focus mostly on continental glaciers. So two existing continental glaciers today, that Greenland and Antarctica, are almost entirely covered with ice sheets that are up to 3,500 meters. That's 11,500 feet, or about 2.1 to 2.3 miles in thickness. That Greenland and Antarctica are both in decline in their net annual growth. The map above shows the elevations of the topography of the ice sheets themselves. So here's your scale, roughly 3,500 meters, and here's the scale on this one. So we have Greenland and Antarctica maps here. So where's Greenland located? Well, you'll see that it's a high latitude. It's near the poles, or near the North Pole. So here's another map here, just to kind of give you a visual or geographic representation. And then here's a few year show. It just kind of illustrates what is taking place here, are the areas in which it's losing. It's getting a net loss of the total glacial ice. And here's Antarctica, just the geography of it. A lot of times you see a map like this, but Antarctica is, when you take a three-dimensional sphere and kind of make it a two-dimensional map, it kind of looks like this, but it really here's what Antarctica looks like, and it is located at the South Pole. So you have these locations of low insulation, low amounts of sunlight, where it's just more conducive to accumulating snow and evolving into these ice sheets. So if we emphasize they're near the poles, they're high latitude regions, right? High latitude, they're near 90 degrees, right, north and south. So what would happen if all of that ice melted? Well, here's a schematic of what would happen if all of today's glacial ice melted. We would have a lot less continental United States. Notice the southeast would be completely inundated with water. And during the glacial maximum, and about 18,000 years ago, when glacial ice was where the ocean water had evaporated and created snow, we've relocated liquid water into the solid form. And here we would see that the United States was actually a lot more. They had a lot more land mass, and you can see that it's actually larger in total geographic. The continent itself would have more landmass. So let's look at the geologic timeline here for the Great Ice Age. That we're really focusing in the Pleistocene. It's generally referred to as the Pliocene Epoch. It's the Great Ice Age's timeline. We've got the Phanerozoic Eon. We would be located in the Cenozoic era. It's in the Quaternary period, and this is the Pleistocene. We're going to be focusing here. This is the Great Ice Age timeline, roughly from 1.6 million years ago to and ended about 10,000 years ago. And here's what this picture here is illustrating. What it would look like where you have these zones of accumulations. You can see these concentric circles, and it's flowing outward under its own weight. We kind of refer to the 65 feet as the depth in which is necessary for this ductile flow under its own weight of gravity and the ice above it. So it begins to flow, and we look at these ice sheets that advanced out of Canada and over our local land. So the Pliocene Epoch, it wasn't just one advance. In the last 1.6 million years, we had 3 different phases, we can call it. We had the pre-Illinois from about 1.6 million years to about 500,000 years ago. That's located in the dark coloration here. And after that, we had a little bit of a time gap, a little bit of change here before the next advance called the Illinois from 300,000 to 130,000 years advancement. That's this lighter shade of gray. And then the lightest shade of gray that influenced our land locally here in northeast Illinois was the Wisconsin. In this case, this advance was about 30,000 to about 10,500 years ago. So this is the one we'll be focusing on. This is what recreated or reshaped our landscape we see today. So how do continental glaciers form, grow, and move? Well, precipitation in the form of snow accumulates to a depth of 65 feet and becomes granular snow, a combination of snow and ice. So later, as more and more granular snow is compacted, the weight of the more snow above it and gravity act together, turning it into firn, a very blue ice. And then air is released gradually, and recrystallization fills in the newly opened gaps and becomes welded together, creating the glacial ice. So we have snow and ice here, we have this firn, very deep blue color, and then we have glacial ice. And glacial ice is very ductile. It can flow at a very, very slow rate, but yet still flow itself. So how does a glacier accumulate this debris, the sediment, these fine silts and clays, these cobbles and pebbles, and boulders even? Well, they pick up sediment at their base and they transport it. So here we can look at the glacier's advance by picking up sediment from the base, the bottom of the glacier, and a conveyor belt-like motion picks up the sediment. It literally pulls it up into itself. So glaciers are really like these dirty ice balls. And the process of picking it up is called plucking. Plucking is the process where meltwater freezes into these cracks and accumulates by freezing to the bedrock. And when the glacier kind of lunges or surges forward, that debris that it was frozen to now becomes a part of it and is mobile with it. So in the picture you can see a diagram of how sediment is accumulated or picked up and transported in the direction of the advance of the glacier. Well, now we have to consider the regimen states of glacial movement. And there's 4 primaries. So it's the regimen state of advancement. That's where the accumulation back here is greater than the ablation or the net loss at its terminus or its end. So we could have a regimen state of retreat. That's where accumulation is less than ablation, that it's melting more than it's growing in the backstage of the accumulation zone. But the one we're going to focus on is the regimen state of equilibrium. This is where accumulation is about equal to ablation. That it's accumulating here, it's still internally advancing, but it's losing at about the same rate. And that's this picture I'll get into here in a moment. And then you have a regimen state of stagnation. That's where it's not advancing internally. And there's a net loss here, that the accumulation is about equal to ablation, that it's really just kind of stagnant. It's literally just melting backwards. So let's go over this picture. In the regimen state of equilibrium, we're going to be looking at moraines in our local landforms. We're located on the Deerfield Moraine. How did these moraines locally form? Well, here's what we have. We have this internal advancement. It's moving this debris and sediment. It could be rocks, could be silt and clay. Remember, it's just a dirty ice ball that's moving over the land. Well, in the regimen state of equilibrium, we say that the accumulation back here, like way back at where it originates, is about equal to the ablation and the net loss. So if it's still internally advancing, it's cranking out sediment that's going to build up. In this case, we're going to be forming a landform called a moraine. And the moraine is going to be, let's just say, silt, clay, rocks, cobble, boulders, all kinds of different sediment sizes. So our landform, our land itself, was formed literally under our feet by this regimen state of equilibrium during the Great Ice Age, when this internal advancement was just cranking out and churning out sediment and leaving it in these mounds. So here we can look at what's called an end moraine in the Wisconsin age and the end moraine in the Illinois stage. So if I look here, the Illinoisan, obviously they traveled, predates the Wisconsin. That's in purple. But the red of what we're going to look at, these are end moraines. These are landforms. These are the terminus or the end of where the glacial ice sheet was at the time that the Wisconsin was in the zone of, let's just say, the regimen state of equilibrium. They're forming land. and they're picking up debris and they're depositing it at the end of it. And so a local moraine map would show this very picture. We have the Valparaiso morainic system. That's the large one that we see in this picture here. But we're located on the Deerfield moraine. And when we take our field trip, we're going to travel from the Deerfield moraine. We're going to head east. We'll travel over the Blodgett moraine, over the Highland Park moraine, and we'll be kind of camped out right here. We're going to head down to Lake Michigan. That our land itself is the direct result of glacial activity. So here we can see that glacial ice does not have any preferential treatment to anything. Even the Mississippi River and all the river systems that were in its path were reworked into the modern day location. Here we can look at Lake Agassiz. In this case here, this is a map showing the extent of the glacial lake. It's an ancient glacial lake. It was about 12,000 years ago. It lasted about 4,500 years. It was an immense feature, bigger than all the present-day Great Lakes combined, that the modern-day remnants of the water are still major landscape features. So there's still evidence that this lake existed. Well, let's talk Great Lakes. How did Lake Michigan and all the Great Lakes form? Well, the evidence shows that the Great Lakes were once just river systems, and those river systems here provided a path for glacial ice to flow through. Ice exploits low land into soft rock. So we could see that continued advances and retreats enhanced the low land, and it later melted. So this lobate shape that we see of Lake Michigan today is very much a characteristic of glacial ice, and it's a land feature, it's a structure, a shape even, that was once these rivers that were just further enhanced by advances and retreats. That the Great Lakes formed when a river system was taken over during the glacial period, and the glacier enhanced the lowland, sometimes a river valley. And the Great Lakes sit on top of soft rock. It's called Devonian shale. And the glaciers carved through it and sculpted the formations we see and eventually melted. So there are multiple glacial readvancements and retreats, and that's how the Great Lakes are believed to have formed. That's what the evidence shows. Well, there were these features that took place historically, and there were glacial ice dams that built up. Here we can see in Washington that some of these glacial dams eventually broke, and it scoured the land and changed it. That Lake Missoula was a proglacial lake created when a lobe of the ice sheet, the Cordilleran, but that's not the biggest deal for now, it dammed up the ice, or dammed up the water, right? There was an ice dam. Periodically, the ice dam would fail, sending huge torrents of water flooding across the landscape in eastern Washington. And so here's a video that illustrates that. I'm not going to show it right now, but it left a landscape. And the only geologic story to this landscape was called a relic feature of what took place during the Great Ice Age. When the ice dams broke, it flooded the land, eroded and deposited, and reworked the landscape. So land features reflect the geologic processes that both destroyed what was there prior before reconstructing them into what we see today.